Welcome to lecture number 3 for ECE 376 Embedded Systems, MPLAB8 and flowcharts. In this lecture we're going to look at how to download code to your PIC and how to describe your code with the flowchart, as well as go through a couple of sample programs. Now to start with, there's a couple ways to download programs to a PIC processor. That's one of the most important parts about any microcontroller, how to get your program on it. There's quite a few different options for microchip. There's a PIC Start Plus. That's kind of what I use when the kits come from DigiKey each summer, and I assemble the lab kits. I take the chips from DigiKey, which are blank, put them in a PIC programmer, and program in the bootloader. You can program anything onto a chip, with something like a PIC Start Plus, and there's many other ways to do that now. What the bootloader does is it makes it more convenient. Rather than having to have a piece of hardware like this, I can program it through the serial port. Now the bootloader is actually programmed on the microprocessor. What it does is on reset, it checks to see, are you trying to download a new program? If it sees a carriage return within the first 3 seconds of reset, it'll clear out the old program and try to download a new one. Otherwise, it starts executing the program at address 800. So the bootloader itself takes up the low 800 spots of memory, which means those are no longer available for you. That's also code protected, so presumably you can't erase it. If your chip refuses to download code after a while, it could be you lost the bootloader. That's not a problem. Bring it in, we'll put a new bootloader on it, or swap it out with a chip that does have a bootloader on it, and it'll reprogram it. That's not supposed to happen, but it does happen 3 or 4 times every semester. When you hit the reset button, again, what you're going to see is the light blinking a couple times. That's the bootloader. For example, if I hit this reset button, this is a PIC board that I use. It's yellow, different than your boards because I'm special. I got yellow boards. I hit the reset button. That starts the program again from address 0, where the bootloader is located. This guy right here, that's the serial port. It's talking to the computer trying to see, is anybody there? If the lights keep on blinking, that's good. This says you've got a program running on your board. That's the bootloader. It's looking for a new program. Next, we'll look at how to download a program to your PIC board. There's instructions online. It's probably easiest to show you in person. And there's a couple of versions of MPLAB you can use. I personally prefer MPLAB8. MPLAB8 is the latest version of MPLAB, and it's been improved to the point it's almost unusable. MPLAB8 is a fairly simple version of it that works great. I recommend using MPLAB8. To start out, I need to go through the project wizard. So I'm going to tell it what processor I have. These are all the processors that are available for microchip. The one we're using is a PIC 18F4620. That's one of like 1,000 different processors sold by microchip. They're all very similar, but there's enough differences you got to specify the right one. This will tell it when I say port A, port B, port C. It'll understand it now that I've specified this processor. The next step, and it's kind of slow when I'm running a recording program at the same time. The next step is you have to tell it which processor you're using. The Universal Tool Suite is the C compiler. We'll use that starting week 5. We're doing assembler. I have to tell it where you want to put the project. Pick some place you can find. I like putting it on a thumb drive. So I'm going to put it on my USB orange thumb drive 376 assembler. And pick a file name. Something that'll inspire the masses. I like the name Jake. It's got a ring to it. And at that point, you've created a project. If I go under View Project, it tells me what the files are, and currently the files are empty. Let's create a program. One of the easiest ways to download a program is to start with a program that works. So if I go to the Bison Academy for sample code, here's like one of the first ones, 1234.asm. I'm going to copy that program, go back to MPLAB, if I can find it. There we are. Paste it in here. On Bison Academy, this is under text file. That's just so you can actually download it. And here I have to give it an extension .asm. So let's call it 1234.asm. And notice the colors change. It now recognizes what is clearf, MOVLW. Those are simpler commands corresponding to this processor. To include that file, I do a right-click, add file, 1234.asm. When you compile, this is what I compile. It doesn't care what you're editing. So oftentimes what I do is first close everything down, double-click on what I'm in the project file. This is what I'm compiling. Make sure I compile what I'm editing. To build it, I do project build, F10. And absolute, I'm not sure it makes any difference. When you build it, it's trying to convert the assembler to machine code. And hopefully what's going to happen is it's going to come up and say, success. So there I just created a list or hex file that I can download. If there's a mistake, like if I have something like this in here, and I hit build, that's also F10, it'll tell me error. I have no idea how to interpret that line of code. So here's an error. I don't know what to do with this line of code. So fix the error, rebuild. And you've created your file. One thing I forgot to do is under Project, Build Options, Project, make sure everything's decimal. Otherwise, if I do something like 10 decimal is different than hex. The default is hexadecimal. So now everything's decimal, and fortunately for this code, that doesn't really matter because the numbers are small enough. It's not going to make a difference. Once I get the hex file, and I can look at it, if I look at the .lst file, this is what the program looks like. Here's the address, here's the machine code, there's the assembler command that I just generated. The hex file, .hex. There's machine code. That's your program. That's what I want to download. To download your code, there's a couple ways to do it. My preference is to use the Nate Zimmerman super amazing see if I can figure out where this is. There it is. Super amazing utility. If you go into resources, it's this guy, the Pick Flash tool. I've already downloaded it. It's a small program I just put on the desktop. You're not supposed to do that, but it's so small it doesn't really matter. Once you get the Pick Flash tool running, you should see the serial port right here, minus COM3. I'll connect to the COM port. Select your hex file. It's 1234.hex. This needs to be lowercase, 8gx. If it's not, you might have to rename it to make sure it's lowercase. Pick that file. When I hit reset, I'll get that 321 message. On 2, it cleared out the old program, waiting for a new one. Hit program, and there it is. Here I've got a equals 1, b equals 2, c equals 3, d equals 4. So that's all you need to do to download your program. And the nice thing that we'll kind of see in a second is if I want to change the program, I just change, recompile, download. Very easy to download a program. The next topic for today is flowcharts. A flowchart is a graphical way to explain how a program works. That's especially important in assembly. Assembly is really cryptic, so a graphical way to explain your program really helps. Now, rule of thumb on flowcharts, it's supposed to help. So keep it simple. If you have more than 20 blocks in a flowchart, it's not really that easy to understand, so it's not really that useful a tool. But keep it informative, so don't just have a single block saying homework set number 3. One block. Have less than 20, more than one block. Kind of explain your algorithm. Another rule of thumb, flowchart should start at the top of the page and flow down to the bottom. That's kind of how the user wants to see it. There should be one starting point and one exit point, ideally. The symbols for flowchart: an oval is the start, a rectangle is a function or an operation, parallelogram is input or output. That's kind of semantics. I could have the operation output data, or have a parallelogram output data. Is that a function or an output? A decision block is a diamond. All these blocks have a single input, single output. If I have two outputs, I need a decision block, because I need to say, is A greater than 0? Yes or no. You can also have multiple outputs. So you can say, what is A? Is it 1, 2, 3, 4? That'd be like a case statement. In terms of the I/O pins on the PIC, there's 33 I/O pins split up into 5 ports. That's port A, B, C, D, E. On your PIC board, those are just sorted, so you have port A, B, C, D, easy to see where the pins are. They can be input or output, and some can be analog or binary. To set up the ports for binary, you need to make 80con1 equal to 15. We'll be talking about that a little bit later when we get to analog inputs. That'll be in a couple weeks. The other ones you need are the port. That defines the pin. 0 is 0 volts, logic 1 is 5 volts. There's also tris. That tells you whether you're input or output. 1 means input, 0 means output, and a port is 8 bits. So I could say, let's take the top half of port B and make it output, 0, 0, 0, 0. Take the lower half, make it input, 1, 1, 1, 1. And I would just have 0F, 0, 0, 0, 0, 1, 1, 1, 1 for tris B. Latch, I really have no idea what latch does. The datasheets say it's a read, modify, write operation on the latch C register. Read and write the latched output value for port C. I have no idea what that means. I've been ignoring it for about 10 years and it hasn't bitten me yet, so I'll keep ignoring it. To start out with the flowchart, let's start with a simple program. Let's just count the edges on port B. The flowchart would just be, or what I want to do in terms of a timing diagram, if here's port B and I push the button, that kind of corresponds to this. If I push the button on port B, it's going to go 0, 1, 0, 1, 0, 1. I want to count every time I push the button. So to do that, what I'll do is have this flowchart. I'll initialize the ports. Port B is input. Port C is output. I'll wait until RB0 equals 0. That's right here. Then wait until it's a 1. If it is a 1, then I just saw a rising edge. Increment port C, and then wait for it to go to 0 again, wait for it to go to 1. That's the flowchart. The corresponding program is this one. Also going to notice in embedded systems, you have this infinite loop. The bottom arrow got cut off, but you typically have an infinite loop in embedded systems. If you build a stoplight, I want it to work over and over again. I don't want it to work just once. Likewise here, this is a counter. It's not going to count just once. It's going to always count how many times you hit the button. And the way the code works, I first have to offset the code by 800. That's to bypass the bootloader. I'll make all the ports output except for port B. Port B is input. That's to move FF to tris B. 1 means input, 0 means output. Everybody's digital. And starting from 0, clearing port C. I'll now go to port B. As long as it's a 1, I'll keep on checking. So if it's a 1, don't skip, 1, don't skip, 1, don't skip. As soon as I go low, then I skip out. While it's low, I'll keep on checking, checking, checking. As soon as it's a 1, I'll skip out and increment. Increment port C, put the result in port C. Then repeat. That's my counter. Now to implement it, what I kind of like doing is go to Bison Academy, start with a code that works. This is the counter, copy paste. I'll now go over to MPLAB, wherever you were. Take the old program that we had, blow it out, and replace it with the new improved code. We'll wait for it to compile. Now that I've recompiled it, I just created a new list file. So now we'll go to the code to download, hit the reset bin. Here's your 321 message, program, and it just blew out the old code. The new code is a counter. So when I hit RB0, notice that the light turns on port B. that means this pin is input, and all of port B is input. So there's pin 2, here's port B pin 3. If I go to port B pin 0, I'm counting the rising edges on port B pin 0. So there's 3 pushes, 4, 5, 6, 7, whole bunch of pushes. That's my counter. A variation on a counter is a random number generator. Here the idea is I'm going to count. Instead of just counting on the rising edges, as long as the button's being held down, I'm going to count really, really fast. As soon as I release the button, whatever the count was, that's my random number. I'm relying on the person to be my random number generator. This will actually do about 1.6 million counts per second, so fast that I can't keep up. It'll just basically count a random spot. That's the timing. What the flowchart looks like is this. I'm going to check, is RB0 equal to 1? If not, skip over. If it is a 1, then yeah, increment the die. In terms of coding, same as before. Port B is input, everybody else is output, everybody's binary. Then here's to do a bit test. If bit test, skip if clear, port B pin 0. If the button's not pushed, I skip. If it is pushed, I'm going to increment die, so 0 goes to 1, 1 goes to 2, 2 goes to 3. Increment die, put it in W, then AND it with 7. This is the mod 8. If I just take the least significant 3 bits, I'm just going to get the number 0 through 7. Put the result in die, move that to port C, and then repeat. What that looks like is the following. I'll go back to Bison Academy and get the random number generator. Put that up on Bison Academy because you could type it in by hand, but a whole lot easier doing copy-paste. Paste in the old program, compile, hit F10. That compiles the new improved code. And hopefully there's no errors. Now that it's compiled, I can download it. Since I didn't change the name of the project, it's going to still be 1234.hex. Download that code. And here's what it looks like. If I hold down RB0, port C is counting really, really fast. That looks like it's got the number 7. It's actually not. It's just counting so fast I can't see the lights blinking. Release the button, and it stopped on 1. So let's roll the dice, release, got a 1 again. Roll the dice, release, there's a 7, roll, release, 1. There's a lot of 1s here. I'm going to guess a 1. Come on, 1. 6. Anyway, that's a random number generator. Last topic is top-down programming. Now, if you're writing a program and you're spending hour upon hour in lab and can't get anything working, it's probably the style of programming. That's part of this class. How do you write a program that you can debug? Top-down is one way to do it. We'll talk about bottom-up programming a little bit later. Top-down says, first, start with the flowchart. Here, if I want to roll a die, what I'm going to do is maybe initialize the I/O pins, check to see if port B pin 0 is equal to 1. If not, display the die. If yes, then keep rolling. The well implemented are subroutines. I'll call the subroutine initialize, and then roll the dice, then display. Each of these will be a subroutine. Fill them in one at a time. Initially, the subroutine will just be a no-op return. It doesn't do anything, but at least the program runs. That way, when you modify the code beyond repair, you know which part of the routine killed it. If you do a top-down, the main routine basically looks like your flowchart. For example, I might have the initialize subroutine being clear tris A, make port B input, everybody else output. There's my initialize routine. The other advantage is I can reuse that subroutine. When I write another program, this will probably look the same. My die roll, I could say I'm going to increment the variable die, put the result in W, add it with 7 to make it mod 8, put the result back in die, and return. Display routine is actually kind of trivial. I will just take the value of die, move to W, move W to port C. I can also do that in one command, movff. That way, if I do that, it should run. What's nice is, suppose instead of rolling an 8-sided die, I want to roll a 6-sided die. Everything stays the same, just change that one subroutine. So top-down programming is a way to write programs that I can check the code. Are my I/O pins initialized? Am I rolling the dice? Am I displaying the value? Check it one by one, and eventually you'll have working code. If you try to write the code all at once and it just crashes on you, it's really hard to debug. So if you're spending hour upon hour in lab, it's probably the style of programming you're using. Try a different style, like top-down, bottom-up. And what a lot of students call it is baby steps. Get your program to work one bit at a time. You first get the I/O pins to work. That's what we did initially. Display the numbers 1, 2, 3, 4. Get it to count. Get it to count when you hit a button. Get it to display the count. Go in baby steps, and you can finish your assignments usually in less than an hour. So that's the third lecture for ECE 376 on how to use MPLAB8, downloading your code, and using flowcharts. We'll next start looking at binary inputs and binary outputs.